Suppose the rod in the figure has a mass of 0.42 kilograms and a length of 20 centimeters, and the current through it is 40 amperes. Part A. If the coefficient of static friction is 0.48, determine the minimum magnetic field, not necessarily vertical, that will cause the rod to slide, and give the magnitude of B. In Part B, we're asked to find the direction of the magnetic field relative to the vertical. In order to solve this problem, I'm going to draw a picture as looking from the side. This horizontal line represents the rails on which the rod will slide, and this circle is an end-on view of the rod itself. This problem contains two subtleties. The first is that the problem uses static friction. As we remember the formula for static friction, this is not an equation in which the static friction is equal to something, but rather it is an inequality, because static friction is less than or equal to μs times the normal force. What this means is that there is only one circumstance in which we can use the value of μs times the normal force, and that is when something in the problem tells us that we are going to reach the limit of static friction. In this case, the operative phrase is just cause the rod to slide. In that case, when we are just causing it to slide, we're able to use the equal sign. The second subtlety in this problem regards the direction of the magnetic field. To understand this subtlety in detail, we can remember a problem that occurred in the first semester of our physics class. And that problem is what it takes to slide a box horizontally against friction. As you'll remember, in the case of that problem, it is not most advantageous to pull the box directly horizontally. The reason is, if you are to instead pull a box with a slightly upward force, you can reduce the normal force and thereby reduce the friction, giving some particular angle that is to your advantage. The problem at hand is exactly the same problem, except we're going to be applying the magnetic force at some unknown angle rather than the force on a string. Because this problem is intrinsically a force problem, we begin it in the same manner that we begin every force problem, and that is by drawing a free body diagram. This dot will represent the bar, and as we list the forces, we see first that we will have mg pointed downward. We will have a normal force pointed upward. The static friction will be directly to the left. And finally, we'll have the magnetic force. And by analogy to the sliding of the block problem, this force will be directed up and to the right. The strength of this force will be ILB, and before we're done with the problem, we will be breaking it into two components. The manner by which we orient the coordinate system in any force problem is with the acceleration. However, this object is not yet accelerating, and so we will orient the coordinate system in the manner that gives us the simplest possible equations. And this will be a vertical and horizontal coordinate system chosen such that we only have to take components of one of our four forces, and that will be the magnetic force. We'll assume that the angle theta is the angle in between the magnetic force and the horizontal, and therefore assign horizontal and vertical components to the magnetic force, and these are respectively ILB cos theta and ILB sine theta. Because this is a two-dimensional free body diagram, it will result in two equations, one in the x direction and the other in the y direction. In the x direction, we'll choose the positive direction to the right, and so the ILB cos theta term will be positive, and the friction term will be negative. In the y direction, we'll choose up as positive, so the ILB sine theta and normal force terms are positive, whereas the gravity term is negative. The two items that we've been asked to solve for are the magnetic field and the angle theta, and so we're going to endeavor to eliminate the normal force from these two equations. We can solve the second equation most easily for the normal force, yielding the result n is equal to mg minus ILB sine theta. This result we are going to plug into the first equation exactly in the frictional term, and that will yield a new result, ILB cos theta minus mu-s mg plus mu-s ILB sine theta. This equation we can solve by grouping the b terms together and then solving for the magnetic field. As shown here, we can do this in two simple steps: first combining the terms, and second solving for the magnetic field. Notice that the equation for the magnetic field does not have an answer at this point. This is because the angle theta is not yet known. However, if we remember the way the problem was set up originally, we are asked to find the minimum magnetic field necessary to start the motion. In this case, the word minimum does not apply to the static friction, but it instead implies calculus. In order to get the minimum possible magnetic field, we need to maximize the term that contains theta in the denominator on the right-hand side of the equal sign. As we remember our calculus, the manner by which you maximize any quantity is you set its derivative, in this case the derivative of the entire quantity in parentheses with respect to theta, equal to 0. Solving this will tell us what value of theta, and then using that theta in the boxed formula will give us our final solution. Let's begin. The derivative of cosine is negative sine, and the derivative of sine is positive cosine. Setting that derivative equal to 0 will tell us the maximum of this quantity and thereby the minimum magnetic field. As you'll notice, this formula solves very conveniently to tell us that the tangent of theta, sine over cosine, should be equal to mu s. Therefore, theta is equal to the inverse tangent of mu s, which gives us 25.64 degrees. This result is in fact the answer to part B of the problem, and furthermore can be plugged into the formula in the box so as to yield our answer for the magnetic field. Substituting in all the known values allows us to calculate our final result, telling us that the magnetic field required is 0.2226. This result is in fact the answer to part A and completes our entire calculation.